Imagine an enterprise network operating at just a massive global scale, right? Like a company like Arroyo Shoes.
Oh, yeah, a major multinational manufacturer, huge footprint.
Exactly. So it's a typical Tuesday afternoon. Thousands of financial transactions are processing every single second.
Right.
Inventory data is flowing from, distribution centers all across Europe straight to retail partners in North America.
Just a constant stream of data.
Yeah, and the C-suite in New York is sitting there reviewing real-time quarterly projections, pulled from servers all the way in Tokyo. The entire corporate nervous system is just humming perfectly.
It's what every IT manager dreams of.
Right. But then, outside their corporate headquarters, a municipal construction crew is, operating a backhoe.
Oh, no. I know where this is going.
Yeah, and with one wrong move, that backhoe completely severs the primary heavily armored fiber optic cable connecting the headquarters to the outside world.
And in a fragile architecture, or frankly, in most networks built maybe 20 years ago, that specific moment is when the entire corporate entity goes completely dark.
Just instantly offline. Thousands of transactions should just halt, right? Distribution centers should lose their connection to the central database. And millions of dollars in revenue are instantly bleeding out.
That's the nightmare scenario.
But at Arroyo Shoes, that catastrophe never actually happens. Instead, the network reroutes all of that global traffic in milliseconds.
Milliseconds, just a blip.
Yeah, the data instantly finds an entirely new path to its destination. It moves so fast that nobody in the C-suite even registers a flicker on their real-time dashboards.
Well, quarterly review just continues like nothing happened.
Exactly. So how does an insentient network of cables and routers intelligently dodge a physical disaster in real time? It's not luck, right?
No, not at all. It is the highly engineered reality of Layer 3 data communications.
And if you are an IT leader, an operations manager, or just anyone who wants their infrastructure to survive a literal backhoe to the primary fiber line, you need to like, subscribe, and share this deep dive right now.
Absolutely.
Do this so you always maintain a competitive edge in the hyper-connected marketplace. Also, you must explicitly check out the description below this deep dive.
We've put some really good stuff down there.
Yeah, we've linked additional corporate resources, highly detailed network diagrams, and essential technical reading for your continued professional education.
Because relying on hope is not a business continuity strategy. Understanding the architecture is.
Totally. So to set the stage for that understanding, this deep dive is Chapter 8, Layer 3 Networking.
A huge topic.
Yeah, this represents a critical pivot in our 15-chapter strategic arc, which is based on the Telecommunications for Managers curriculum.
Right. And to briefly bridge the gap from our last session, Chapter 7 dealt strictly with Layer 2 networking, right?
Yeah, we examined endpoint connectivity, network segmentation, collision domains, and Ethernet LAN topologies.
So basically, we looked at how devices talk to each other when they're sitting on the exact same physical local segment.
Right. Layer 2 is essentially the local neighborhood.
Yeah.
It handles the physical moving of electrical signals or light pulses from one switch port to another using physical MSAC addresses.
And this is the key, a MAC address has absolutely no concept of geography.
None. Which brings us to the mission for today's deep dive, which is bridging academic networking principles with high-level corporate decision-making.
We are moving from the local endpoint connectivity of Layer 2 to the absolute undisputed core of inter-network engineering.
The network layer.
Exactly, the network layer. This is where disparate, isolated islands of data are connected into a cohesive, globally resilient enterprise.
So where does this fit in the Open Systems Interconnection model, the OSI model? And what is its baseline function?
Well, the network layer, Layer 3, sits right in the middle of the OSI stack. It's positioned below the transport layer, which is Layer 4, and directly above the data link layer, Layer 2.
Okay.
And its absolute primary function is path determination and logical addressing. It's basically responsible for moving data across a series of interconnected, vastly different networks.
So if Layer 2 is like a delivery truck driving down a specific street.
Right. Layer 3 is the global logistics network calculating the entire route from a factory in Shenzhen all the way to a warehouse in Chicago.
Wow.
Yeah. It uses logical addresses, IP addresses, mostly, to completely abstract away the underlying physical hardware.
But wait, if Layer 4 is prepping the data for transport and Layer 2 is handling the physical movement on the actual cable,
yeah,
Layer 3 sounds like this massive middleman that would just create a huge bottleneck. what is physically happening to the data when it hits layer 3?
Oh, well, two incredibly resource-intensive processes happen here: encapsulation and fragmentation. Let's start with encapsulation.
Okay, so lay it on me.
When an application sends data, it passes down the stack, right? The transport layer takes that data, adds its own header, say a TCP header to ensure reliable delivery, and creates a segment.
Right, the segment.
Then it hands that segment down to layer 3, and layer 3 then takes that entire transport layer segment and treats it purely as payload.
It just wraps it up.
Exactly. It encapsulates it by wrapping it inside a new structure called an IP datagram, or, a packet. It slaps on a layer 3 IP header.
I want to visualize this header, actually. Are we just talking about a sender and receiver address, like writing on a physical envelope?
Well, the source and destination IP addresses are definitely the most critical components, yeah?
Yeah.
But an IPv4 header is this highly complex 20-byte structure.
20 bytes just for the header.
Yeah, it includes a version field, a header length field, a type of service field, which is crucial for quality of service, by the way.
Like prioritizing executive OIP calls over standard email traffic.
Exactly that. And it also contains a time to live, or a TTL field.
Time to live. Wait, why does a packet need an expiration date?
To prevent it from circulating the globe infinitely. You see, every time an IP packet passes through a router, the router decreases the TTL value by 1.
Oh, I see.
So if that TTL hits 0 before reaching its destination, the router just drops the packet and sends an error message back to the source. It's a fundamental failsafe against infinite routing loops.
Okay, so encapsulation is the process of building this highly detailed IP envelope around the data. It's like the logistics manager packing a crate.
Yes.
But you mentioned fragmentation earlier, which sounds inherently, destructive. Why is a network deliberately breaking apart the data it's actively trying to deliver?
Because of the strict physical limitations dictated by Layer 2?
The local roads, so to speak.
Right. Every physical medium, whether it's standard Ethernet, Wi-Fi, or fiber optic, has a strict rule about the maximum size of a frame it can transmit.
And what's that called?
That's called the maximum transmission unit, or MTU. For standard Ethernet, the MTU is typically 1,500 bytes.
Let me stop you there for a second. What happens if the application in Layer 4 generate a massive payload, and Layer 3 encapsulates it into an IP datagram that is, say, 4,000 bytes long?
Right.
It hits Layer 2, and Layer 2 says, I can only carry 1,500 bytes at a time. What happens?
That is precisely when Layer 3 must perform fragmentation. The router's processor actually has to halt the forwarding process.
It just stops.
Yeah, it has to slice that 4,000-byte datagram into 3 separate fragments. And then, and this is the heavy part, it has to create a brand new, slightly modified IP header for every single fragment.
Wow. How does the receiving end even know how to put it back together? I mean, if I get 3 random pieces of a letter, I need to know the order.
This is where specific fields inside that IP header come into play. Specifically, the identification, flags, and fragment offset fields.
Okay, how do they work?
The identification field gives all 3 fragments the exact same unique ID number, so the destination knows they belong to the same original packet.
That makes sense.
The fragment offset tells the destination exactly where this specific piece belongs in the sequence. And the flags field has a bit called more fragments.
Let me guess. The first 2 packets have that bit turned on.
Exactly. The first 2 have the more fragments bit set to 1, telling the receiver, keep waiting, there is more. The final packet has it set to 0.
So Layer 3 on the destination side collects all these pieces, looks at the offsets, reassembles the 4,000-byte datagram, and only then passes it back up to Layer 4.
Correct. That's exactly how it works.
That seems like an unbelievable strain on corporate infrastructure.
Mm.
I mean, if we are running a global video conferencing platform or pushing terabytes of financial data,
Oh, it is.
doesn't this constant slicing and reassembling cause latency? Are we introducing lag into a board meeting just because the packets are too big?
It is a massive managerial concern. Excessive fragmentation introduces severe latency. The routers along the path are forced to use their own CPU cycles and memory to manage the fragmentation process instead of just forwarding traffic.
They're doing math instead of moving boxes.
Right, but the real danger is packet loss.
How so?
Well, if a 4,000-byte datagram is fragmented into 3 pieces, and just one of those 1,500-byte fragments is dropped by a congested router, the destination cannot reassemble the packet.
Oh, wow. So it just drops the other 2 pieces and asks for the whole 4,000-byte payload again?
Yes. The entire original datagram must be retransmitted. In real-time applications like voice and video, this results in catastrophic jitter and dropped calls.
That's unacceptable for an enterprise.
Which is why senior enterprise network engineers invest heavily in path MTU discovery.
What's that?
It's a protocol that probes the entire path from source to destination to find the smallest MTU limit along the way. Then it forces the sending application to size its packets to that exact specification right from the start, avoiding fragmentation entirely.
Oh, that's smart. You want the shipping crates to be the exact right size for the smallest delivery van on the route before they even leave the warehouse.
Perfect analogy.
Okay, so that clarifies the data formatting. But to organize this massive global logistics operation, we have a terminology distinction that constantly trips up even experienced IT professionals.
I know exactly what we're going to say.
Yeah, we need to distinguish between routed protocols and routing protocols.
The confusion stems entirely from the fact that they sound identical, yet they serve completely separate architectural functions.
So break down the distinction for me. What is a routed protocol?
A routed protocol is the cargo. It dictates the formatting of the data being transported across the network. It provides the logical addressing scheme that allows a packet to be forwarded from one network to another.
Right.
When we talk about the envelope with the source and destination addresses, we are talking about a routed protocol.
So the Internet Protocol IP is a routed protocol.
The Internet Protocol is the undisputed, universally adopted routed protocol of modern networking. Whether we're discussing the older IPv4 or the newer IPv6, they are the routed protocols. They are the data being moved.
Okay. Then what on earth is a routing protocol?
Routing protocols are the intelligence. They are the underlying algorithms, the GPS systems that routers use to communicate with each other.
So they don't carry the actual email or video stream.
No, routing protocols do not carry user data. They carry network topography data. They allow routers to dynamically discover which paths are available across a massive global architecture.
Oh, I see.
And then mathematically calculate the single most efficient route to a destination.
To make sure I'm totally grasping this, the routed protocol is the IP datagram carrying the CEO's email.
Right.
And the routing protocol is the algorithm that determined the email should travel through the fiber link in London rather than the satellite link in Tokyo.
That is the exact functional distinction. Examples of routing protocols include Routing Information Protocol, or RIP, Open Shortest Path First, OSPF, and Border Gateway Protocol, BGP.
And they constantly talk to each other to build a dynamic map.
Exactly.
And that map is stored in a routing table.
Yes, it is.
So if I am an IT director looking over an engineer's shoulder, and they pull up a routing table on a core switch, what am I actually looking at? What am I analyzing?
A routing table is essentially the router's internal ledger. It is the definitive source of truth for where data should go. If you execute a command like show iproute on a Cisco enterprise router, the operating system outputs the current state of that ledger.
Walk me through the anatomy of a single entry in that table. What are the specific columns of data I'm seeing?
First, you'll see a protocol code, a letter like C for directly connected, S for a manually configured static route, or O for a route learned dynamically via OSPF.
So it tells you how it learned the route.
Mm-hmm.
This indicates the origin of the intelligence.
Yes, because some sources are more trustworthy than others. Next, you see the network ID and the subnet mask. This is the destination network.
Okay.
Following that is the forwarding address, often referred to as the next hop IP address. This is the IP address of the very next router in the sequence.
Wait. It doesn't know the whole path to the destination?
Typically, no. A router only cares about the next hop. It operates on step-by-step forwarding. It essentially says, look, I don't know the exact layout of the destination city, but I know this packet needs to go to the router in Chicago next, and Chicago will figure out the rest.
That sounds remarkably short-sighted for such an intelligent system.
It's actually highly efficient. If every router had to calculate every single jump for the entire internet, the processing overhead would literally collapse the network.
Oh, sure. I guess that makes sense.
So after the next hop IP, the table then lists the outbound physical interface port, such as Gigabyte Ethernet 01, where the packet should actually be ejected. And finally, it lists the routing metric, the mathematical cost of using this specific path.
What happens if a packet arrives that the router looks at the destination IP, scans this entire ledger, and finds absolutely no match? Does it just drop the packet?
Well, in a poorly configured network, yes. But an enterprise-grade routing table will always contain a default route, often termed the gateway of last resort.
The gateway of last resort.
Yeah. It is a catch-all entry, usually designated by the IP address 0.0.0. It acts as the postmaster rule. If the destination is entirely unknown, forward the packet to this specific upstream router.
Which usually points toward the internet service provider.
Exactly, assuming the ISP's massive core routers will know where to send it.
I want to challenge something from the source material regarding these protocols. The curriculum explicitly mentions that some protocols are non-routable.
Yes, they are.
It specifically flags DHCP, the Dynamic Host Configuration Protocol. If the entire purpose of Layer 3 is to route data across networks, why in the world would engineers design a protocol that intentionally cannot be routed?
Because routing certain types of traffic would cause a global denial of service attack.
A global attack, just from DHCP.
Absolutely. We have to look at how local configuration protocols function. DHCP is designed to automatically lease IP addresses to endpoint devices when they join a network, right?
Right.
When an employee opens their laptop in the corporate lobby, the laptop has no IP address. It cannot communicate a Layer 3, so it sends out a massive Layer 2 broadcast message.
A broadcast message meaning it just screams to every device on the local switch, hey, I need an IP address.
Exactly. Well, to be precise, it uses a destination MANT address of all Fs, which hardware switches are forced to flood out of every active port. If that DHCP broadcast message was a routable protocol, the local router would pick it up and forward it to the next router.
Which would forward it to the next.
Yes.
So every laptop connecting to a Wi-Fi network anywhere in the world would send a broadcast that echoes across the entire global internet.
It would be an exponential broadcast storm. It would consume 100% of the world's bandwidth in a matter of seconds. Therefore, non-routable protocols are strictly confined to their local broadcast domain.
It's just incredible.
Yeah, the router acts as a hard boundary. When the router receives that DHCP broadcast on its local interface, it processes it if the router itself is acting as the DHCP server, or it explicitly drops it. It will not forward it.
So this architectural boundary is what keeps local administrative chatter from destroying the enterprise-wide area network.
Precisely. The router is both a bridge and a firewall for administrative noise.
Now, once we differentiate the data from the algorithms, we have to examine exactly how those algorithms make decisions. You mentioned the routing metric earlier, the mathematical cost.
Yes.
When a router is staring at two completely different paths to the exact same data center, what specific metrics does the routing protocol use to declare one path better than the other?
Path determination relies on a variety of metrics, and different routing protocols prioritize different variables. The most archaic, yet simplest metric is hop count.
Hop count meaning literally counting the physical routers between source and destination.
Yes. It simply counts the number of intermediary routers, or hops, a packet must traverse. If path alpha requires going through 2 routers and path beta requires going through 5 routers, a protocol relying solely on hop count will permanently lock onto path alpha as the superior route.
But wait, path alpha might consist of aging 10 megabit copper wire from the 1990s, while path beta could be a brand new 100 gigabit fiber optic backbone. A metric that only counts the number of devices is completely blind to bandwidth.
Which is exactly why enterprise networks rarely use hop count as a primary metric anymore. It is a severe limitation of early distance vector protocols like RIP.
Oh, I see.
To solve this, modern routing protocols utilize more sophisticated metrics. One is load, which actively measures the amount of bandwidth currently in use on a specific link.
So it measures traffic congestion.
Yes. If a primary path is heavily congested, a protocol factoring in load can dynamically reroute traffic over a physically longer but currently empty secondary path.
That's much smarter.
Another critical metric is delay, which measures the cumulative transit time of the links. It factors in the actual physical transmission speed of the media.
Oh, like satellite versus fiber.
Exactly. A satellite link might have a massive bandwidth capacity, but the sheer distance to orbit introduces a massive delay metric, making it highly undesirable for VoIP traffic compared to a terrestrial fiber link.
Right, because nobody wants a 2-second delay on a phone call. Now, there is another term in the sources that sounds more like corporate politics than a mathematical metric. Administrative distance. How does a router calculate trust?
Administrative distance, or AD, is a critical concept for IT managers to grasp because it is the ultimate tiebreaker in a complex network.
Okay, give me an example.
Imagine your enterprise router is running both OSPF and RIP simultaneously, perhaps because you recently acquired a company running older hardware.
That happens all the time.
Right. So the OSPF process calculates a path to a database and says, go left. The RIP process calculates a path to the exact same database and says, go right. The router cannot put both conflicting instructions into its routing table.
How does it decide which algorithm to believe?
It checks the administrative distance. AD is a pre-configured integer value that ranks the reliability of the source of the routing information. The lower the AD, the higher the trust.
So lower is better.
Yes. For instance, a directly connected physical network has an AD of 0. It is absolute truth. A statically configured route, manually typed in by an engineer, has an AD of 1.
Because the router assumes the human engineer knows best.
Precisely. OSPF typically has an AD of 110, while RIP has an AD of 120. Therefore, if OSPF and RIP present conflicting paths to the same destination, the router will always install the OSPF route into the routing table because 110 beats 120.
It trusts the OSPF algorithm more than it trusts the RIP algorithm.
Exactly. It's a hierarchy of trust.
Let's tie this back to the opening scenario with Arroyo Shoes. The backhoe cuts the fiber line. A physical link is dead. How quickly do these metrics adapt? What is the actual mechanism that prevents the network from just throwing packets into a black hole?
The mechanism is network convergence. When that backhoe severs the line, the router directly connected to that fiber immediately detects the loss of electrical signal or carrier light on its interface.
It knows instantly.
It instantly flags that path as dead in its own routing table. But it cannot stop there. It must warn the rest of the enterprise. It immediately generates emergency routing update packets and blasts them out of every other active interface to its neighboring routers.
Spreading the news of the failure.
Yes. Those neighboring routers receive the update, recalculate their own metrics, update their routing tables, and forward the alert to their neighbors.
A domino effect.
Convergence is the state achieved when this wave of recalculation has finished, and the routing tables of all devices in the entire internetwork are fully synchronized once again. They all share the exact same updated, accurate map that reflects the loss of that fiber line.
And the goal for a corporate IT department is to drive that convergence time down to milliseconds so the end-user applications never time out.
That's the gold standard.
Now, what if the router calculates that there are two perfectly equal paths to the same destination? The metrics match identically. Does it just pick one randomly?
No, an intelligent router will utilize equal cost load balancing. If two links offer the exact same metric to a destination, the routing protocol will install both paths into the routing table.
Okay, so both are active.
Right. As packets arrive, the router will divide the traffic, forwarding packet 1 down path A, packet 2 down path B, and so on. It is the equivalent of opening multiple lanes at a toll plaza during rush hour. It doubles the effective bandwidth and prevents bottlenecks.
We're talking extensively about how routers find the fastest path, but enterprise managers often care more about controlling what is allowed down those paths.
Oh, absolutely. Security and prioritization.
Yeah, the curriculum outlines traffic flow management using access control lists, or ACLs, breaking it down into packet forwarding, packet filtering, and traffic shaping.
ACLs are the enforcement mechanism of corporate security and QoS policies. Packet forwarding is the default state. If the router knows the path, it sends the packet out the designated interface.
Waving the employee through the checkpoint?
Right. Packet filtering is the intentional interruption of that process. An administrator writes a sequential list of rules, the ACL, and applies it to a router interface. As a packet attempts to enter or exit that interface, the router pauses. It dissects the IP header and the transport layer header.
It's inspecting the cargo.
It inspects the source IP, the destination IP, and the specific application port. If the ACL contains a rule stating, deny any traffic coming from the guest Wi-Fi subnet trying to reach the payroll server IP, the router physically drops the packet and refuses to forward it.
Turning away someone without a badge.
Yeah.
And traffic shaping. How's that differ from just blocking or forwarding?
Traffic shaping uses ACLs to classify data and enforce priority queues, often using algorithms like the token bucket or leaky bucket. Instead of just blocking traffic, shaping dictates bandwidth allocation.
Give me a real-world enterprise example of where an operations manager would demand traffic shaping.
Well, consider a multinational hospital network. They share a primary WAN link for all traffic. The IT manager will use traffic shaping to guarantee that radiological imaging data and real-time surgical VoIP communications are flagged with the highest priority.
Critical data.
Yes. If the WAN link becomes congested, the router will intentionally queue and delay bulk email traffic or employee web browsing to ensure the critical medical data never experiences a dropped packet.
It's a VIP fast lane. The delivery trucks and standard traffic are forced to idle on the on-ramp, while the ambulances get a dedicated clear lane.
That's a great way to look at it.
This brings us to a massive divide in how these routing networks are actually architected. We need to dissect the two primary categories of routing intelligence: distance vector protocols versus link state protocols.
This is a fundamental architectural fork in the road for any enterprise network design. Let's begin with distance vector, or DV, routing protocols, the most famous legacy example being the Routing Information Protocol, RIP.
How does a distance vector protocol actually see the network? I assume it builds a massive map.
No, it builds no map at all. This is its defining characteristic.
Really? No map?
No. A distance vector protocol only possesses two pieces of information about any given destination: the distance, which is the hop count, and the vector, which is the specific local interface port it must use to send the packet in that direction. The router is completely blind to the overall topology of the network.
If it doesn't have a map, how does it know where anything is?
It relies entirely on hearsay from its immediate neighbors. Every 30 seconds, a router running RIP will take its entire routing table and broadcast it out to all its directly connected neighbors.
Okay.
The neighbor receives that table, adds one to the hop count, and incorporates that information into its own table.
It's quite literally the telephone game.
Yeah.
Hey, router A told me it can reach the database in 2 hops. I am 1 hop away from router A, therefore I can reach the database in 3 hops.
That is exactly how the Bellman-Ford algorithm, which powers distance vector routing, operates. It is routing by rumor.
That seems incredibly vulnerable. What happens if router A loses its connection to the database, but before it can broadcast the failure, router B sends a routine update saying, "Hey, router A, I can reach the database in 3 hops."
You have just identified the count to infinity problem, which results in a catastrophic routing loop.
Oh boy.
Because router A lost its original path, it receives router B's update and thinks, "Excellent, router B has a path. I will route my traffic through router B." Router A updates its table to say it is 4 hops away, routing through B.
But router B's path was routing through router A in the first place.
Yes. Router A sends the data to router B. Router B looks at its table and sends it back to router A. The packet bounces back and forth at near light speed, consuming all available bandwidth. As they continue to exchange updates, the hop count metric will increment to infinity, completely crashing the network segment.
That's a disaster. How did engineers historically solve this? The sources list several timers: hold-down timers, invalid timers, and something called split horizon.
To mitigate routing loops in distance vector environments, engineers had to implement complex rules. A hold-down timer forces a router to freeze an entry in its routing table if it hears a network has gone down.
So it just stops listening to updates for a bit.
Exactly. It refuses to accept any new writing updates about that specific network for a set period, giving the entire enterprise time to organically learn about the failure before accepting potentially false looped information.
And split horizon, what's that?
Split horizon is a fundamental, almost philosophical rule of network trust. It dictates that a router must never, ever advertise a route back out of the specific interface on which it originally learned it.
Meaning?
If router B learned about a path from router A, router B will completely filter that specific path out of any updates it sends back to router A. It breaks the loop before it can even form.
I understand the mitigations, but if distance vector is this fragile and blind, why don't we look at the alternative? How do link state routing protocols like OSPF Open Shortest Path first operate differently?
Link state protocols reject the routing by rumor concept entirely. Instead of passing around completed routing tables, link state protocols are designed to track the actual real-time status of every individual link in the network. Is the link active or inactive? What is the connection type? What is the bandwidth speed? What is the delay?
How does it gather that data without just asking its neighbors?
It does ask its neighbors, but it asks for raw data, not calculated routes. Routers running OSPF generate tiny data packets called link state advertisements, or LSAs.
LSAs, okay.
These LSAs contain the real-time status of the router's own directly connected links. The router floods these LSAs out to the entire network. Every single router collects these LSAs and compiles them into a massive, highly detailed topological database.
So every router builds its own localized satellite imagery of the entire corporate infrastructure.
Precisely. Once a router has compiled this exhaustive database, it independently runs Dijkstra's shortest path first algorithm.
Stop right there. Dijkstra's algorithm is legendary in computer science. Can you explain the fundamental math of how it actually calculates the road?
Sure. Edsger Dijkstra developed this algorithm to find the shortest paths between nodes in a graph. In our context, the nodes are the routers, and the edges are the physical cables connecting them.
Right.
The algorithm initializes by assigning a tentative distance value to every node in the entire network. It sets its own local distance to 0, and it sets the distance to every other router in the enterprise to infinity.
Because it hasn't mapped the paths yet.
Right.
It assumes everything is infinitely far away.
Right. It then looks at its immediate, unvisited neighbors. It calculates the physical cost, the bandwidth metric to reach them. If the calculated cost is less than the current recorded distance, which is currently infinity, it overwrites the value.
It updates the map.
It then marks its local node as visited and moves to the neighbor with the lowest calculated cost, treating that neighbor as the new center of the universe, and repeats the process.
So it iteratively fans out across the entire topological map, calculating the cumulative cost to every single node, until there are no unvisited nodes left.
Yes. And because every single router in the OSPF area has the exact same LSA database, every router runs the exact same Dijkstra mathematical calculation, resulting in a perfectly synchronized, loop-free understanding of the best path to every destination. Every router has identical situational awareness.
If link state gives every router perfect, synchronized situational awareness, why would any IT manager ever allow a distance vector protocol like RIP on their network? Why operate in the dark?
That is a critical question of resource allocation and overhead. Link state protocols are architecturally superior, but that intelligence demands a massive toll on hardware.
They require heavy lifting.
Absolutely. Maintaining a synchronized topological database of thousands of enterprise links requires substantial memory. Continuously running Dijkstra's complex mathematical algorithm every time a link state changes requires massive CPU processing power. And flooding the network with LSA updates consumes raw bandwidth.
So for a massive enterprise data center, the routers have the silicon to handle it. But what if we were talking about a small retail branch with a 20-year-old router sitting in the back closet?
OSPF could completely overwhelm the CPU of an older edge router, causing it to freeze and drop traffic. In highly limited small-scale environments, the low overhead simplicity of RIP's distance vector approach was historically advantageous.
Historically.
Right. However, to be clear on modern enterprise strategy, RIP is essentially obsolete. It scales incredibly poorly and should not be deployed in modern architectures.
So what are corporate engineers actually deploying today?
If a corporation operates a strict, single-vendor network comprised entirely of Cisco hardware, they often utilize AI-GRP-enhanced Interior Gateway Routing Protocol. It is an advanced protocol that acts like a hybrid, using distance vector mechanics but incorporating link state features for rapid convergence.
But if they're a multi-vendor environment, they have Cisco core switches, Juniper Edge routers, and Arista data center gear.
Then OSPF is the absolute undisputed standard. It is an open standard protocol supported by every major vendor globally. Both OSPF and EIGRP are classified as interior gateway protocols. They manage the routing exclusively inside your corporate network, which is technically termed an autonomous system.
What happens when the data needs to leave the autonomous system? When our internal corporate network needs to route traffic out onto the public internet? OSPF doesn't run the internet, does it?
No, OSPF would collapse under the weight of the global internet's routing table. To cross the boundary between completely separate organizations like Arroyo Shoes connecting to AT&T, you require an exterior gateway protocol.
Which is?
The single protocol that holds the entire internet together is BGP, the Border Gateway Protocol. It is a path vector protocol designed specifically to handle massive scale and enforce complex corporate routing policies between different autonomous entities.
We have spent a lot of time analyzing these dynamic protocols algorithms that automatically adapt to failures. But there is a completely different approach that corporate managers sometimes demand: static routing.
Static routing is the rejection of algorithmic autonomy. It is the managerial demand for absolute manual control over data flow.
So dynamic protocols auto-heal the network. If link dies, OSPF recalculates. With static routing, a human administrator physically logs into the router and manually types in a command that says, to reach network X, you must always send the data out interface Y.
That is correct.
But if interface Y gets cut by a backhoe, the static route doesn't recalculate. The router just drops every packet into a black hole until a human logs back in and changes the code.
Right.
Why would an enterprise executive ever accept that level of operational fragility?
For 3 reasons: absolute predictability, strict security, and resource preservation. The curriculum highlights highly sensitive environments, defense contractors, government agencies, and core banking systems.
Places where security is non-negotiable.
Exactly. Imagine a financial institution with a heavily encrypted, dedicated fiber optic link connecting their primary data center to their disaster recovery site.
They're syncing millions of financial transactions.
They absolutely do not want a dynamic routing protocol like OSPF accidentally deciding to reroute that highly classified transaction data over a public internet VPN just because a metric fluctuated on the primary line. The risk of data interception or a violation of compliance regulations is simply too high.
So they use a static route to essentially nail the connection to the floor. The data travels over the dedicated fiber line, or it doesn't travel at all.
Yes, manual paths prevent dynamic protocols from accidentally routing secure data through compromised, unmonitored, or suboptimal links. Furthermore, static routes require 0 CPU cycles to calculate and generate zero routing update traffic.
Which preserves 100% of the link's bandwidth for the actual financial payload.
Precisely.
Let's apply this to a real-world troubleshooting scenario from the source text to see how engineers manage these paths. The text introduces a network engineer named Arturo. He's troubleshooting a connectivity failure.
Right, the Arturo scenario.
Yeah, he is sitting at the source router trying to reach a destination server, but the connection is failing. He executes a standard ping command to the destination. The ping times out. What is Arturo's next analytical step?
Arturo is facing a classic Layer 3 diagnostic challenge. A ping timeout only tells him the complete round trip failed. It doesn't tell him where it failed. He must isolate the directionality of the failure. To do this, he runs an advanced diagnostic command. An ICMP debug internet control message protocol debug on both the source router and the destination router simultaneously.
Because an ICMP ping consists of two parts, right? An echo request going out and an echo reply coming back.
Correct. By watching the live debug logs on both routers, Arturo observes something critical. The debug log on the destination router registers the arrival of the ICMP echo request.
Wait, so the packet successfully traversed the entire network and hit the destination?
Yes. The destination router received the request and attempted to generate the ICMP echo reply, but Arturo is still not receiving that reply back at his source console.
The outgoing Layer 3 forwarding worked perfectly. The failure is entirely isolated to the return path. It's like sending a registered letter. The recipient signed for it, the destination debug proves it arrived, but the return receipt got lost in the mail on the way back to you. The problem isn't the outbound route, it's the inbound route.
That perfectly illustrates the concept of asymmetric routing. In complex enterprise environments, the path a packet takes to reach a destination is often completely different from the path the return traffic takes to get back. Arturo's troubleshooting proves that he doesn't need to investigate the outbound routing tables. He needs to trace the inbound routing tables hop by hop from the destination back to the source to find the missing route.
Arturo's scenario highlights a fundamental reality for operations managers. Links fail, routing tables get misconfigured, and hardware dies. But in a modern digital enterprise, downtime is unacceptable. It costs millions. This brings us to the executive mandate for Layer 3 resiliency and redundancy.
Resiliency is the architectural capability of a network to maintain a defined quality of service regardless of physical faults, power failures, or cable cuts. Redundancy is the physical implementation of that resiliency. It is the duplication of critical components.
So if I walk into a Fortune 500 data center, what does true redundancy look like across the layers?
You must architect redundancy in a tiered approach. First, you address physical media, Layer 1. This means deploying duplicate, hot-swappable power supplies in every chassis, massive, uninterruptible power supply battery banks, and diesel generators on the roof.
If the city grid goes down, the silicon keeps spinning.
Yes. Second, you build Layer 2 access redundancy. You deploy duplicate core switches and duplicate distribution switches. You wire multiple connections from every server to multiple switches.
But hold on, we established earlier that Layer 2 doesn't have a TTL, a time-to-live field. If you plug two switches into each other multiple times, won't that instantly create a catastrophic Layer 2 broadcast loop?
It absolutely will, which is why Layer 2 redundancy is useless without implementing the spanning tree protocol, specifically Rapid Spanning Tree Protocol, RSTP, or Multiple Spanning Tree Protocol, MSTP.
What does that do?
Spanning tree mathematically analyzes the physical loops and logically blocks redundant ports, keeping them in a standby state. If the primary link fails, Spanning Tree instantly unblocks a redundant port to restore connectivity without causing a loop.
That's brilliant. So you have redundant power and redundant switches. What about Layer 3? How do we back up the routing intelligence?
This is where we deploy first hop redundancy protocols, or FHRPs. This is software resilience. Consider a floor of 200 corporate employees. Their laptops are all configured with a specific default gateway, the IP address of the local router that connects them to the internet.
If that single physical router experiences a hardware failure and catches fire, those 200 employees are completely offline. The redundant switches don't matter if the gateway to the internet is dead.
Which is why an enterprise deploys multiple physical routers and links them using an FHRP, like the Open Standard Virtual Router Redundancy Protocol, VRRP.
How does VRRP magically fix a burned-out router?
It uses abstraction. VRRP clusters two or more physical routers together to form a single logical virtual router. This virtual router is assigned its own virtual IP address and its own virtual MAC address. The IT department configures all 200 employee laptops to use this virtual IP address as their default gateway rather than pointing them to physical hardware.
But who is actually doing the processing if the router is virtual?
Behind the scenes, the VRRP protocol holds an election. One physical router is elected the master. It assumes the virtual MAC address and actively forwards all the traffic.
And the others?
The second physical router becomes the backup. It sits in a hot standby state, continuously listening for a heartbeat signal from the master.
What happens when the master router physically loses power?
The backup router misses the heartbeat. Within milliseconds, it triggers a failover process. The backup router instantly assigns the virtual IP and virtual MC address to its own physical interface. It broadcasts a gratuitous ARP message to the layer 2 switches, effectively saying, the virtual MST address you are looking for has moved to my port.
And the 200 employee laptops?
They notice absolutely nothing. Their default gateway IP hasn't changed. Their TCP IP connections remain intact. The traffic simply shifts to the standby hardware seamlessly. In a Cisco-exclusive environment, the proprietary equivalent to this is HSRP, the Hot Standby Routing Protocol. By combining this virtualization of routers with redundant physical chassis, you completely eliminate the router as a single point of failure.
But I have to ask the ultimate managerial question, the question the CFO is going to ask. Architecting this level of redundancy buying duplicate core routers that cost tens of thousands of dollars, paying for alternate fiber lines, trenching into the building from completely different streets, installing diesel generators, it doubles the capital expenditure of the entire IT budget. How does an IT manager justify buying expensive equipment that is designed to sit idle in hot standby 99% of the time?
You never frame the conversation around the cost of the equipment. You frame the conversation around the mathematical cost of an outage. It is a strict business continuity calculation.
Walk me through that calculation.
If a massive e-commerce retailer loses their primary layer 3 routing core, their website goes offline. The operations manager must calculate the exact revenue generated per minute during peak operational hours. If the site generates $50,000 a minute, a 30-minute routing outage costs the enterprise $1.5 million in permanently lost revenue, not including the reputational damage and SLA penalties.
Wow. When you put a $1.5 million price tag on a 30-minute outage, suddenly writing a $100,000 check for a redundant standby router and a VRRP deployment seems incredibly cheap.
It transforms an IT expense into a high-yield insurance policy. Enterprise executives must understand that highly engineered redundancy is not a luxury. It is a fundamental requirement for corporate survival.
Which brings us to the definitive managerial takeaway of this deep dive. Layer 3 is not just the mechanical transport of data. It is the highly intelligent, resilient brain of global corporate operations.
That's perfectly stated.
When a physical disaster strikes like the backhoe severing the primary fiber cable outside Arroyo Shoes, it is the complex mathematical calculations of OSPF, the instant convergence metrics, and the seamless failover mechanisms of VRRP that save the company. They ensure the data instantly finds a new path, the supply chain continues to function, and the business never skips a single beat.
It is the invisible architecture of modern commerce.
So we now understand how data mathematically finds its way across the globe and how we build resilient, fail-proof paths. But how do we actually manage the identity and security of the thousands of individual laptops, servers, and smartphones connecting to this massive network? Well, that is the exact managerial puzzle we are solving in our next session. Chapter 9, Network Infrastructure Implementations.
IT leaders must understand the edge. We will be analyzing how core infrastructure services, specifically DHCP, IP address management or IPAM, and network access control, NAC, establish absolute enterprise asset visibility and granular security containment at the edge of the network.
You absolutely need to stay tuned for that strategy session. So once again, hit subscribe, like this deep dive, and explicitly check out the description for the highly detailed resource links and network diagrams. Furthermore, review the channel for our other corporate IT playlists designed for your continuous professional education. I highly recommend diving into the Digital Forensics series and the Network and Systems Security Deep Dive modules hosted right here on the channel.
Before we close, let's tie this entire architectural discussion back to the Schuessler concept of security system strategy. We spent this entire session examining how Layer 3 trusts routing metrics. We assume the LSA database is accurate. We assume Dijkstra's algorithm is calculating reality. But what happens to an enterprise when a malicious actor infiltrates the internal network and intentionally injects fake link state advertisements? What happens to your business continuity when a hacker mathematically deceives the OSPF algorithm into routing highly classified corporate data straight into a compromised trap? How secure is the intelligence of your network when the map itself is a lie?
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.